the session topic is novel application of foodomics, and I'm happy here to introduce well-renowned experts here in the field of foodomics. Yeah, and foodomics probably some of our speakers will introduce you to the topic, which is sort of shortly comprehensive analysis here of the metabolome that is present in food. And we'll start with, let's say, traditionally, I would say we need to start here in Bavaria with beer. And I'm happy to introduce our first speaker to you. So it's Stefan Pietsonka. And he's a food chemist by training here, coming from the Technical University of Munich. And he'll present to us the results of, partly the results of his thesis that he already submitted and will defend soon here at our university. And I'm happy to announce the topic of his talk is Archeochemistry reveals the first steps into modern industrial brewing. And Stefan, the floor is yours.
Okay, so thank you, Professor Rychlik, for the nice and kind introduction. Yes, I will start the session within the field of fermented beverages. We later will also hear about wine oxidation, but I will also focus on a more German traditional beverage, beer. And I also will take you on a little time travel, I would say. So archaeochemistry, applying analytical chemistry on archaeological or historical samples, it reveals the first steps into modern industrial brewing. You will hear about a beer sample from the German Empire era, so exactly that time when industrial brewing has taken its first steps. Let me begin with this description of this very interesting and unique sample we had the pleasure to analyze. So in 1885, the Bavarian Brewery in Lübbecke, in northern Germany, they had a contractually agreed collaboration with the Lloyd Shipping Company. We know from historical sources that every year over 300,000 beers, sealed and waxed, left the German Empire. However, one of those beers never left mainland Germany. It was found in the late 20th century in a commercial building. So from this historical background, from the very elaborate closure of the beer and its label design, we here see a very recent picture of the beer sample and its replica. We know that this beer dates back to exactly that time when Bavarian was available in Asia and in India, in America, and the whole world market. So what time exactly are we now talking about? I will also focus on the engineering and scientific breakthroughs during that period when pioneers like Hansen, Pasteur, Linde really paved the way for modern science and modern food production. So the concept of fermentation, the concept of microorganisms was discovered. Filtration was made available on an industrial scale, and the first refrigerating apparatus was invented by Linde. This had an immense impact on what we are nowadays used to, what is normal for us nowadays. The concept of food hygiene was established. In the 1880s, then Hansen was able to isolate the first single yeast cells and grow the first yeast cultures. There are no real written historical sources remaining about that, but the Bavarian Brewery, they claim to have owned one of these refrigerating apparatuses as early as 1881. About this shipping contract we already talked, and now 130 years later, building up on and rising from all this pioneer work, we have the pleasure to analyze this particular sample with most modern analytical chemistry. So what exactly did we analyze? Which instrumentation did we use, and how did we draw conclusions? I will start with the more classical, traditional brewing science analytics, targeted analytics, before then heading to NMR spectroscopy and later mass spectrometry. So these beer characteristics, they were analyzed using the supernatant here of the beer bottle. We analyzed the color, bitterness, alcohol content, pH value, real extract, attenuation limit, and also the folate content. The sediment then was used for microbiological testing. So we tried to cultivate different microbes on many different cultivation media. The beer was microscopically examined, and we tried to find genetic information that might point towards specific microorganisms. These brewing parameters we analyzed, they were, despite this very long storage time of decades, quite similar to what is known for beers brewed at that time and analyzed at that time. We have very old literature available here. Interestingly, the alcohol content, with about 4 volume%, still was quite high. On the other side, the bitter units, comparatively low. So this already indicates that there might have been some change in hops compounds, oxidation, storage effects. These storage effects we can also see when looking at the color. So this beer is quite dark, and the folate content is very low. So these light and oxidation unstable folates, they already degraded. Microbiology, unfortunately, did not show any cultivatable microorganisms, which is very sad. We were not able to find yeast cells or cell structures under the microscope, and we were not able to find microbe DNA by very sensitive qPCR. The only thing visible were these amorphous organic particles that come from polyphenol and protein complexation. So what does this tell us now? First of all, we can say, according to the brewing parameters, this beer is quite well preserved. It is definitely extensively filtered, which is not very self-evident during that time. We have no signs of spoilage effects, no signs of contamination with wild yeast, with microorganisms. However, there are some aging indicators already that we analyzed then using a different analytical approach, the non-targeted metabolomics approach. So traditional archeochemistry, it more so targets on specific molecules, specific markers that might indicate something. For example, tartaric acid as indication of winemaking, oxalic acid coming from germination, which is maybe an indicator for brewing, lactic acid, acetic acid as spoilage indicators. So what we try to do now is to rise these investigations on a more holistic level, combining many different non-targeted analytical techniques to make this full sky of metabolites, this full sky of molecules available. So let's see what this sky of metabolites has in store for us. The historical beer was analyzed by means of high-field NMR spectroscopy, ultra-high resolution FT-ICR-MS mass spectrometry, and liquid chromatography coupled ToF-MS. We first started with NMR spectroscopy, where we have the structural information about our molecules, where we can identify molecules, we can quantify molecules without any ionization biases. And we have a very wide range of chemicals available. So here we decided to compare the 1H NMR spectra of the old beer on the bottom compared to its modern equivalent, so the Bare Pilsner beer as it is available right now on the market. From the first overview, we can already say the signals look quite similar. The pattern is quite similar. So this indicates that most of the metabolome probably is quite persistent. So the alcohols, ethanol, methanol, isobutanol, isopentanol, the organic acid, citric acid, maleic acid, malic acid, pyruvate, amino acids, fatty acids, all of that was found in very comparable amounts. The carbohydrates here, the pattern was quite similar as well, but we find more reducing alpha ends in the historical beer. We find more Maillard reaction derivatives like coibios. So all of this points towards some oligosaccharide degradation here. The polyphenols, similar pattern as well, but lower concentration in the old beer due to this complexation we already saw under the microscope. Overall, these spectra are very similar, but there are some clear ravages of time that we can resolve with this analytical technique, especially in the chemical shift area of of aldehydes. So in this part of the spectrum, we, for example, see two interesting signals, 30 and 31, that are present in high amounts in this old beer and not really visible in modern brewing. These signals, they belong to furfural and hydroxymethylfurfural, HMF, both of which are very well-known Maillard reaction markers. We also determined the concentrations here and found concentrations far higher than what is known in brewing literature. Especially here, the furfural concentration, it was extremely high. As comparison, the shipwreck beer, which was found about 10 years ago, which also dates to the 1840s about, here they found 0.66 milligrams per liter of furfural, so it's not even close. This beer definitely is a very unique source of a well-preserved beer sample that has been subjected to decades-long storage, but under very moderate conditions, so not under the seawater. Another interesting molecule here in this part of the spectrum is niacin, also known as nicotinic acid or vitamin B3. Here we have concentrations of 6.2 grams per liter. Modern beers have about 1,000th of that concentration. So where does this big gap now come from? First of all, yes, our quantification is valid, as a very old literature confirms. Niacin, it is stable throughout the brewing process and also during storage. It is not produced during fermentation, but it correlates with the gravity of the beer, which means it somehow has to come from the barley. Norris et al. Back in 1945 already noticed that the niacin content in the beer decreased over the advancing industrialization of the brewing process. The cultivars, the barley cultivars themselves, however, they did not change in their nicotinic acid concentrations. So it is quite nice to exclude all of these solutions, but where's the answer now? Well, niacin is known to be accumulated in the germ of the barley grain. So thus we conclude that after the malting process, this germ is not really carefully removed in historical brewing technology. We also had a closer look on fermentation byproducts, such as acetaldehyde, formic acid, acetic acid. All of those were higher in concentration in the historical beer, which might be attributed to either less controlled fermentation environments or maybe also simply the different yeast used at that time. Interestingly, the lactic acid concentration now, it was lower in the historical beer. One would assume that maybe due to lack of food hygiene, there might have been some spoilage with lactofermenting microorganisms, but no, again, no sign of any spoilage. There even is an explanation why the lactic acid concentration is now lower compared to modern brewing. In modern brewing, we try to optimize pH values of the wort of the mash to get better protein breakdown, to get better enzyme activities. In order to do so, we add sour wort, which simply is lacto-fermented wort. We add lactic acid to our beer. So this knowledge, these little subtleties were not known back then in historical brewing. No pH optimization. Concluding now with NMR spectroscopy, I will come to mass spectrometry with a focus on direct infusion, Fourier transform, ion cyclotron resonance mass spectrometry. Here we also have a wide range of molecules available with highest mass resolution and highest mass accuracy. Here's a simple scheme of such an instrument. In short, after ionization, so for example electrospray, the ions get transferred through the ion optics into this so-called ICR cell, which is surrounded by a big superconducting magnet, just as we know it from NMR. Inside the cell, the molecules, they rotate. The heavier they are, the slower they rotate. So this is simply the simplified concept of this instrument. And Let me now maybe demonstrate the advantages that come with this mass spectrometer. Here we see a mass spectrum in the Metabolomics range, so from 0 to 1000 Dalton, of a conventional ToF-MS. When we now zoom in until we come to a nominal mass here, so mass of 317, we see some signals that overlap quite a bit and are not that easy to interpret. When we now rise the quality of such a spectrum to the level of FT-ICR-MS, we see very nice and very sharp resolved mass signals. Indeed, we can find here over 40 mass signals inside this historical beer only in the nominal mass of 317. So all of them share this mass but differ in the decimal places. Due to the accuracy of our mass measurements, we can also assign a unique molecular formula to each of these signals. So we can, for each molecule, say out of which atoms it is made up. That's very important for the later interpretation of our data. So how to utilize this information now? We can plot our molecules, for example, in such a so-called Van Crevelen diagram, where we plot on the y-axis the H/C ratio of our formula, so hydrogen number over the carbon number, and on the x-axis, oxygen over carbon. And like that, we can define specific areas where we would expect certain molecules. For example, carbohydrates, they have a lot of oxygen, they have a lot of hydrogen, they will be appearing here. Lipids, on the other side, very saturated as well. Not that much oxygen, lipids are located in this area. And like that, we can plot the about 4,000 molecular signals we have for this modern beer compared to just about 5,000 we find in the historical beer. One area that drew our particular attention here, it's not that easy to see, is this area of the Maillard reaction. So Maillard reaction of carbohydrates with amino compounds, with amino acids. And during this reaction cascade, reaction network, we oftentimes have a loss of water, a loss of H2O in the carbohydrate structure. So the carbohydrates, they slowly move towards the bottom left in this diagram. That's why we call this Maillard reaction area. And here we see a lot more CHO compounds in the historical beer. So the blue dots, CHO meaning only carbon, hydrogen, and oxygen inside the structures. Compared to here. I admit it's not that easy to see, but I will sum up on the next slide. If one is interested in more detail about Maillard reaction in brewing, I may refer to our food chemistry paper where we were able to describe this reaction network in more detail with thousands of different Maillard reaction products. But what we definitely can agree on is that the Maillard reaction, it is very dependent on reaction conditions. So despite the fact that the beer we found was comparatively dark, we would maybe compare it to a Munich type of beer, so dark lager beer. Despite this fact, its Maillard reaction chemical space is very different from such a Munich type of beer. When we have a lot of heat, high temperature in short time, we get a lot more CHNO compounds, so nitrogen involved in our structures. On the other side, when our beer is stored for decades, with very, very moderate conditions, we have a lot more CHO compounds. So overall, yes, we have a lot of Maillard reaction inside our beer during the storage, but it's very different from roasting Maillard. We have no roasted malt in our beer. Coming back to the Van Crevelen diagrams, I plotted here some molecules that we were able only to find in the historical beer, not in the other ones. Some molecules that also indicate oxidation and staling of the beer, so oxidized lipids, oxidized hops bitter acids. Starting with the lipids, lipid oxidation is very well known for beer staling. There is such a thing like the nonanol potential, which means the potential the beer has to form nonanol out of linoleic acid, which gives a bit of a cupboard off flavor to the beer. And of course, linoleic acid is not the only acid that oxidizes. So indeed, these about 200 oxidized lipids, we were able to connect them to each other in what we call a mass difference network. So here, every of those molecules is connected to each other according to specific biochemical or chemical relations. And with very simple redox chemistry, we can come to very oxygenated structures here. So 8 oxygens inside LC-16 structure. So this beer definitely is a very unique source for the oxidation chemistry in brewing and of storage effects. We cannot really recreate something like that with forced aging experiments or something. For the bitter acids, inside this mass difference network, the connections that were most abundant also were oxygenations, which confirms our hypothesis of extensive oxidation reactions inside this chemical compound class. Also, the fact that the signals for the well-known hops bitter acids like isohumalone, the alpha acids, beta acids, these signals, they decreased about 98%. So there's hardly anything left of these compounds we know. But we have about 400 different derivatives that were created during the storage. And interestingly, it's worth noting that over 95% of these compounds don't have any hit in any database and are not known in brewing literature. Not a single hit, not a single compound. So again, this beer is a very unique source for insights in the oxidation chemistry of hops bitter compounds. Now we will move away a little bit from looking at specific compounds or compound classes and more concentrate on the whole chemical fingerprint FT-ICR-MS provides. In order to do so, we have to utilize chemometrics tools. We have to utilize statistical description of our big chemical data. In our case, supervised OPL SDA, so orthogonal projection to latent structures discriminant analysis. In order to do so, we analyzed more than 400 different modern brews as a training set and then projected the position of our beers with unknown characteristics, namely this historical beer and its modern equivalent as a checkup. So the first model, it differentiates beers brewed with bottom fermenting yeasts on the left against beers brewed with top fermenting yeasts. Both of the beers bottom fermented, which is quite interesting because back then bottom fermentation was not that easy. These yeasts, they prefer temperatures of below 10 degrees Celsius, so the fermentation tank needs to be cooled, which is possible, for example, in the winter by using ice, which is not very elegant when you want to export your beers. Or you can use the newly invented refrigerating apparatus. A quick side note here, maybe many of you, or some of you might already know, yes, indeed, literally the first fridges were invented to chill beer. And one of those may have been available to the Bavarian brewery. It is very plausible. The second model differentiates beers that were brewed according to the German Purity Law, or back then Bavarian Purity Law, against those that aren't compliant. So those that use malt extracts, sugars, starch, syrups, different kinds of herbs, flours, stabilizers, antioxidants, you name it. Both of the beers here are compliant with the Purity Law. However, the statistical parameters here are not as good as for our other models. That's why we decided to then add another level of verification. We focused more on the maybe most critical point, which is which starch source was used. So we can differentiate here between wheat in our beer, corn, rice, and barley only. Both of the beers, again, barley only. As we have gathered some experience in the last years with metabolite signals, metabolite networks of different starch sources inside beers, we added then a third level of verification, which is LC-ToF-MS. So again, mass spectrometry, but now with liquid chromatography. So we have available isomeric distributions, and we have more structural information available by tandem mass spectrometry. Here I may refer to our Frontiers paper where we were able to find whole metabolite networks of wheat, corn, and rice metabolites inside the final beer, both on a compositional level, so here FT-ICR-MS mass difference networks, and also on a structural level with tandem mass spectrometry similarity networks. In the end, we were also able to identify specific molecules that are specific for the different types of grains used and that we can target. And of course, we screened our beers for exactly those targets. To say that first, none of these grain metabolites were found in our beers, in the historical beer not, and in the modern beer as well, which is quite nice for the Bavarian brewery. So, for example, the phytoanticipins here of the wheat plant, so wheat plant defense molecules that in the end we can find in the beers. They are present in beers brewed with wheat, but not in our beers. The hydroxyoxandole acetic acids, which is quite specific for the use of corn, and also these specific corn lipids were not found, and as well a marker that we described, the aspartic acid conjugate of oxandole 3-acetic acid and glucoside. The small one here, present in rice beers, not present in our beers. So we definitely can say that the historical brewers at Barre, they brewed their beer according to the Purity Law. Which now brings me to the conclusion of our forensic archeochemical approach. So we were able to show that barley is the only starch source which was used. During the malting process, we have moderate temperatures, we have no roasting malt inside our beer, and after the malting process itself, the germ was not very carefully removed like we would do it nowadays. During the mashing, we don't see any adulteration as well, so carbohydrate patterns are very similar. There are no signs of dry hopping inside this beer. And for the wort, we can say no lactic acid inside there. We have no pH optimization. Then the fermentation, it was quite controlled, but with a bit more fermentation byproducts. And after the fermentation, we have this extensive filtering process, which is very unique for beers at that time. So besides nicely describing now this brewing process, the different analytical techniques, they confirm that this beer, which was found, is very well preserved. However, there are some clear molecular signs, molecular patterns for decades-long storage. For example, the hops bitter acids oxidation, the lipid oxidation, Maillard reaction, oligosaccharide breakdown, folates, and so on and so forth. So this beer definitely is a very unique source as well for storage, oxidation, staling chemistry in brewing, but it still is a very unique source as well for the historical brewing process in that time when modern industrial brewing has taken its first steps. With that, I would like to end my talk. I would like to thank our teams, I would say, at the Chair of Analytical Food Chemistry at TUM, and also where Philip also is located, the Helmholtz Center Munich. the collaborators, and of course the Barre Brewery that gave us access to this very unique beer sample. And of course, I want to thank you for your kind attention.
Yes, thank you. Thank you, Stefan, for the great, let's say, overview on the beer metabolome here and the challenges, of course, for assessing the beer metabolome and the solution that we already have found here, and the insights into, say, technology here as an authenticity assessment of this important food.